Alright, welcome everyone to this video. We're going to talk about ideal and ideal dilute solutions. Okay, so here we're going to start talking about mixtures of solutions. Right. So first talk about ideal solutions. Okay, we're going to start saying, okay, the chemical potential of a pure liquid A is going to be given by mu A star. Okay, so the little star is just indicating the pure liquid. Right, that pure liquid has some vapor pressure at a given temperature, right? And again, if we recall, right, the chemical potential of the gas phase, right, the chemical potential of that gas, of that vapor, is just equal to the standard chemical potential at 1 bar plus RT ln of P, okay? So the chemical potential of a pure liquid is equal to the standard chemical potential of that substance at 1 bar in the gas phase plus RT ln of the partial pressure of the gas of that pure liquid. Okay, right? And again, why those are equal, right, is because again the vapor pressure, right, that is established above gas is related with when the chemical potential of when the chemical potential of your liquid equals the chemical potential of your vapor, right? So that's how we know the chemical potential of your liquid, of a pure liquid, has to equal mu naught plus RT ln PA, right? Because that is the chemical potential of your vapor, right? And that has to equal the chemical potential of your liquid, right? Assuming you've established this equilibrium where you have this vapor pressure, right? And so, yeah, so that is the standard chemical potential of a liquid, right? Now, if we assume that the solution contains some solute, right, then the chemical potential of that liquid is still going to be related with the vapor pressure of that liquid, right? It's just now going to have a different equilibrium vapor pressure, okay? So I got rid of the star, right? The star is for the pure liquid. Without the pure liquid, right, we just have PA, okay? Right? And so if we subtract these two equations, right, two equations for the pure solvent here and for the mixed solvent, right, we get that the mixed, right, this is for the mixed chemical potential, right, is equal to the pure chemical potential plus RT ln of PA over divided by PA star, okay? But again, PA is the vapor pressure in the mixed solution, and PA star is the vapor pressure in the pure solution. All right, and so this leads us to our first discussion here of ideal solutions. And ideal solutions are solutions that satisfy Raoult's law. Okay, so a solution that obeys Raoult's law is a solution that is considered an ideal solution. Okay, well, what is Raoult's law? Raoult's law says that the vapor pressure of a liquid is equal to the mole fraction in the solution phase times the vapor pressure of the pure liquid. Okay. Now note, right, we've talked before, right, that say the vapor pressure of a gas, PA, is equal to the mole fraction of that gas times its total pressure, right? This type of relationship is true for any gas, right, real ideal, right, where this mole fraction here is in the gas phase, right? So here, what we're saying in Raoult's law, right, is that the vapor pressure of the liquid, right, so the partial pressure of the gas above my liquid is equal to the pure partial pressure, the vapor pressure of the pure liquid times the mole fraction of the liquid in this mixture, okay, which is an approximation, okay. This is definitely an approximation to say that PA over PA star equals the mole fraction in solution, okay. So we're going to be talking about these mixtures of liquids, okay. We're going to be dealing with mole fractions in solution and in the gas phase, and X is going to be used for the solution phase mole fractions, Y will be used for the gas phase mole fractions, okay. And again, this defines an ideal solution, Okay, an ideal solution has no interelectric forces between the solute and solvent. Okay, and that's how we can get this relationship. Okay, just by assuming no interelectric forces. Okay, right, and so this holds for both the solute and the solvent, right? So an ideal solution, right, has the total pressure kind of obeying this this chart or this figure here on the right. Okay, where it's just sum of the partial pressures, right? And the partial pressures are just linear slopes, okay? Linear lines, right? Where the slope of that line, okay, is just really the mole fraction, right? Okay, right? And then the intercepts are really with the pure liquid vapor pressures. Okay. So using Raoult's law, right, and our in general, right, so this equation here is for any solution, right? This is a real solution answer, okay? It's assuming ideal gases, but in the solution phase, it's assuming nothing, okay? Right, so again, this is for any type of mixture of liquids, real, ideal, however, right? Now, using Raoult's law, we now are assuming it's an ideal solution, in which case this equation just simplifies down to the chemical potential of the mixture equals the pure chemical potential plus RT ln of the mole fraction of A. Okay. And again, this Raoult's law tells us we're dealing with an ideal solution, right? The ideal solution is a solution that obeys Raoult's law. Okay. An example of this might be, say, mixing benzene with methylbenzene, right? These molecules are very similar to each other in terms of their intermolecular forces, right? And so this kind of mixture basically obeys Raoult's law on all compositions, right? And again, here it's not that there are no intermolecular forces between these things, but basically the intermolecular forces are almost identical between solute and solvent, solute, solute, and solvent, solvent. So this thing's going to behave like an ideal mixture, okay? Because there's no changes in intermolecular forces between things, right? And this is not a very common thing, okay? Most mixtures are not ideal, but for lots of mixtures, what we will be able to use is we can use Raoult's law to approximate the solvent, the solvent's chemical potential for that mixture in a dilute solution. Okay, so if we assume the mole fraction of our solute is very, very small, then Raoult's law holds pretty well for the solvent. We'll talk a lot more about that. We'll talk about ideal dilute solutions, right? Which is now, right? So an ideal dilute solution is a solution in which the solvent obeys Raoult's law and the solute obeys Henry's law. Okay, that is the definition of an ideal dilute solution. Okay, and so what that means, right, is the pressure of the solvent is really the mole fraction of the solvent times the vapor pressure of the pure solvent. Okay, and for the solute, the pressure of the solute is equal to the mole fraction of the solute times Henry's law constant. Okay, Henry's law constant is just some constant that is empirically derived, right? You have to do it through experiments, okay? And it's typically very different from the vapor pressure of the pure liquid, okay? And you get that by basically just plotting the vapor pressure of your liquid with respect to the mole fraction of that liquid and extrapolating that figure. So for example, right, we have our ideal solution, right? So this is our ideal solution, okay? On the right, we have carbon disulfide and acetone being mixed together, okay? And we've plotted the vapor pressures of those guys, right, for what is obviously not an ideal solution, right? And you see, though, okay, what's plotted here are some dashed lines, right? And you see that near the x and y, or near 0 and 1 mole fraction, okay, these things behave relatively linearly, right? And that linear relationship is based off the mole fraction, right? So for example, we have the mole fraction of carbon disulfide, right? So near zero acetone here is going to be behaving as the solvent, okay? And so it's going to satisfy Raoult's law. Here, right? Where in this case, right, the pressure of acetone is going to equal the mole fraction of acetone times its vapor pressure of the pure liquid. Okay. While carbon disulfide is very dilute, and so this is going to satisfy Henry's law, right? And so its pressure, right, of carbon disulfide, I'll call it PC for carbon disulfide, related to the mole fraction of carbon disulfide times Henry's law constant, Kc, okay, which is different, right? Here, when the mole fraction of carbon disulfide is near 1, right, this is satisfying Raoult's law, right? And so you see that the slope is different here near 1 than it is near 0, right? And that slope is related to the difference between, right, the pure liquid vapor pressure and then the Henry's law constant, which is just some empirically derived constant, okay, that you get from plotting something like this and extrapolating out, okay? Right. Right, and so again, right, at so here this figure's plotting what I was kind of showing, right? But plotting out now the straight lines you get from Henry's law as well as Raoult's law, right? It kind of shows you, right, that at 0 versus 1 mole fractions of chloroform here in acetone, right? One thing will obey Raoult's law while the other will obey Henry's law, right? And neither will obey Henry's law or Raoult's law at the same time, right? And it's only near these extremes of near 0 or 1 mole fractions, right, where you get this behavior, right? Near like 0.5 mole fractions, neither acetone nor chloroform obeying Raoult's law or Henry's law, right? They're doing something completely different, okay, right? Right. Okay. So, right. So we've talked about then from Raoult's law, right, what we can get for the chemical potential of the mixture. Okay. And so let's assume we have, say, ideal liquids that we're mixing. Okay. Right. Before mixing, we have, right, the total Gibbs free energy is just equal to the chemical potentials of the pure substances, right? Then after mixing, we're going to use Raoult's law, okay? So that the chemical potential of A is just equal to the, pure stuff plus the number of moles of A times RT times natural log of the mole fraction of A, which again, I'm using Raoult's law at this point, right? I'm assuming Raoult's law to put that mole fraction in there, okay? So using that for A and B, okay, right, you get this delta G of mixing, right, has this very familiar form that we saw for an ideal gas, right? It's the same thing for an ideal liquid, okay? So again, just like an ideal liquid or ideal gas, right, then delta H of mixing is equal to 0, right? And then delta G of mixing is purely an entropy-based thing. Right. But again, this is only true for ideal liquids, right? Which is not most liquids, okay? Right, and again, what makes a liquid ideal or not is related with the fact that you have intermolecular forces between molecules A and A, B and B, and A and B, right? And the only way a solution is ideal is if those intermolecular forces are the same between all three kind of pairs, right? Okay. And so a real solution, right, those things will not be the same. So the enthalpy of mixing will not equal 0, right? And then the entropy of mixing, right, may be smaller than that of an ideal solution, because for a non-ideal solution, right, you might not have this pure, nice, equal mixture of everything across your solution, right? And so the entropy change might be less than that of the ideal case. Okay. And in which case, right, there can be instances where the free energy change, right, becomes greater than 0, right? And so that means that things actually would spontaneously separate from each other, right? Which is obviously what happens when you mix things like oil and water together.